In this video, we're looking at exponential functions. An exponential function is a function of the form f of x equals c times a to the x, where c is called the initial value. It's basically your y-intercept, and then a is our growth factor, or sometimes called the common ratio. What makes exponential functions unique and interesting is that we have our input or our variable as the exponent of our function, rather than being in the base somewhere. Now, there's a few things that you need to consider when you're talking about exponential functions. The base of your exponential function needs to always be positive, and it also can't be 1. The reason why it can't be 1 is that doesn't give us a very interesting function. If you have 1 to some power, that's always going to be 1, so it doesn't really do much for us. It's not very interesting. And also, our initial value is not going to be equal to 0. And for a similar reason, if our initial value was 0, then that just means 0 times anything is going to be 0. And again, not a very interesting function. So an exponential function is going to be in this form. Again, the base is positive, and it can't be 1. And then the initial value cannot be 0. So yeah, a is the growth factor. We also call it the base of our exponential function. So let's take a look at an example of determining whether or not a function is linear or exponential. So we want to know, is this function that we're given from this table of values linear or exponential? And then we want to write the equation for the appropriate function. So to figure this out, what we're going to do is we're going to look at the rate of change. We know that if a function is linear, that it has a constant rate of change. And so we want to know if that is the case. So in this case, we see that all of our x values are increasing by 1, right? Increasing by 1 for all of these. And if it's going to be linear, then that means that the change in the y's is also going to be constant. So to get from 1/4 to 1, we add 3/4. To get from 1 to 4, we add 3. To get from 4 to 16, we add 12. And to get from 16 to 64, we add 48. And so you can see pretty clearly that 3/4 over 1, 3 over 1, 12 over 1, 48 over 1, this rate of change is not constant, which means that our function is not going to be linear. So let's see if it's exponential. To determine whether it's exponential or not, we have to figure out, is there some value that we can take this output and multiply by to get this value? And if that value is the same for all of them, then we know it's exponential. So to go from 1/4 to 1 through multiplication, we would have to multiply 1/4 by 4 to get 1. So in order for this to be exponential growth, then that means that to get to the next value after this, again, we would have to multiply by 4. And 1 times 4 is, in fact, 4. And then 4 times 4 is 16. So we can multiply by 4 here. And then 16 times 4 is 64. So it does look like the y values here are increasing by a factor of 4. So this does appear to be an exponential function. So now we have to write the equation for the function. So remember, if you recall just on the last slide, we said that exponential functions are in the form h of x equals c times a to the x. So we need to figure out the value of c, which is our initial value, and the value of a, which is our growth factor. So again, c is the initial value, or another name for that is the y-intercept. So if you recall, the y-intercept happens when the x value is 0. And you can see that in this function, we are actually given of x value of 0, so we can pretty easily look at the y-intercept. So the initial value is going to be 1 here. What is our growth factor? Well, the growth factor is just the number that you multiply by to get the next value in your function. So we saw that to go from 1/4 to 1, we were multiplying by 4. And then from 1 to 4, again, multiply by 4 times 4 times 4. So that makes this value of 4 the value of a, our growth factor, or the base for our exponential function. So we have the value of c, we have the value of a, which means we can then put these together to give us our exponential function. So h of x equals c, which is 1, times our value of a, 4 to the x power. Now, this is a perfectly fine expression, perfectly fine equation, but we don't really need this 1 here. If you want to keep the 1 there, that's okay, because it does tell us the initial value or the y-intercept right off the bat. But we can also get that by just plugging in 0 for x. So another perfectly appropriate version of this, an equivalent form, is h of x equals just simply 4 to the x power. So that would be our exponential function.